you very much. Yeah, hi everyone. I will talk today about my PhD results that I currently or recently published. And but actually, I'm head of the department at Fraunhofer ILT in Aachen, and I would like to thank during my PhD thesis a few people that supported my work, as namely my students Luke and Niels, and as well Eric and Philip, who did one part where we cooperated with the Max Planck Institute. A few words to Aachen, where we are located. It's a very nice environment, the campus Melaten in Aachen, close to the RWTH University. And talking about digital photonic production, we have, there are two main buildings where we cooperate with industry, in the industry building, namely, for example, company Trump, but also in the research building with the university RWTH, and Fraunhofer is kind of in the middle or in between, transferring the fundamental research to industrial needs. And oh, that was too fast, sorry. And yeah, the department that I'm leading at Fraunhofer with is equipped with a lot of LPBF machines, 20 namely, and in terms of people, we have 17 scientists, a lot of PhD students, thesis students and support from students to support our work in laser powder bed fusion. But as I mentioned, I will not talk about the department, but a little bit of the research I've done in the past. And I will concentrate today about the influence of the shielding gas flow on the results in terms of material development or process development, and also about the influence of carbon content in high-speed steel. Generally, high-speed steels as a tool steel is very interesting for a lot of applications. We heard some work of different tool steels, namely hot work or cold work steels are also investigated in laser powder bed fusion. But high-speed steels have the advantage of having a very high hardness or temperature resistance up to 600 degrees Celsius. And they have been investigated in the past. The material that I'm focusing on today is the HS6-5-3-8. It's a random number you think of, but if you look at the chemical composition, mainly the carbon content is interesting because it's already 1.3%. Talking about shielding gas flow, so just a little bit on fundamentals. We know that in laser powder bed fusion, we generate a lot of byproducts, metal fumes, spatters, powder particles, everything is moving. So maybe looking at the video will help a little bit. The powder is sucked into the melt pool, metal fume is generated, spatters are there, and the melt itself moves a lot as well. And we need the shielding gas flow to prevent any interactions with the laser of those byproducts, to enable a reliable and reproducibility process. So I used an Econity machine in the study, standard samples, I would say, standard exposure strategy as well. So I'm not going into detail here. Talking about the shielding gas flow will be interesting. It's not the material focus, I think, of everyone, but I'd like to talk about the system technology we're using for investigating materials because it's very crucial. So this is the setup of the Econity machine that we used. It's actually as delivered, except those guide vanes that we integrated ourselves, because we have here a three-part where the gas flows inserted, and then the inlet nozzle, and to help the shielding gas flow a little bit to move around 90 degrees, we integrate those guide vanes just by thinking that it might be beneficial. And that is the first shielding gas flow setup that I had that I used with the guide vane inserts and the inlet nozzle. So you can see it from different perspective. As I mentioned, the 90-degree is a little bit challenging, talking about the shielding gas flow. And I will go further into detail why we use the second setup that you're seeing right now here. It is a little bit different on how to move the shielding gas of those 90 degrees. We have a pressure wedge, we call it, and we also integrated a bypass, which supports the shielding gas flow as well. We used simulation for that, but I don't want to go deeper into detail here. But there are two pictures that show why we are doing it, because if you initially have those guide vanes, we see that here's something happening that we don't want. We want the homogeneous shielding gas flow moving along our process chamber. And here we see it's moving up, so might not be very good. And also we have a lot of turbulences here. Looking at the pressure wedge that was developed at ILT, we see higher speed of the shielding gas flow, first of all, because of the narrowing space we have, and also we see straight direction over the shielding, over the platform, which should be beneficial for our project, for our process. We looked into that with videos. So here you can see the setup one that we've used. Here we have a material, it's zinc, so it tends to generate a lot of fume. And you can see that it's not flowing exactly out. You can see there is some fume going up, and then right in the direction where we actually want to manufacture the parts. And here on the right side, you can see with the setup 2 that it is already a little bit or a lot better and less interaction, you can see. Yeah, it's just a schematic if you haven't been able to see it with the contrasts here, but that's how those two setups were working. And we used those two setups to investigate the HS6-5-3-8. And how did we do it? We have an experimental setup. Our material needs to have preheating. So in previous process parameter studies, we found that using preheating of 350 degrees enables crack-free processing of those of this very high carbon content steel. So we were very happy that we are able to process it crack-free. We just used this one process parameter over the whole platform and printed 15 samples. And looking at the setup 1 and 2, you can see that by exposing those 15 samples, looking on the top of those parts, that you can already see that there is an influence over those exposure order, and the surface is a little bit not as shiny as in the beginning for the setup 1. And for setup 2, you can even see that we have might be a lot of energy input we have at the last cube still, that it has such waves along the surface. So it seems that the surface quality depends on those two shielding gas flow setups. And we even went a bit further and changed the exposure direction with the shielding gas flow, because previously you saw the standard exposure direction always against shielding gas flow to prevent interaction with byproducts. If you go in the exposure direction with the shielding gas flow, you force them maybe to interact a little bit. And if you look it up, you can see that it's not as you cannot see it as much as before that there is an influence, but there's still a little bit uneven surface compared to the one with the setup 2. So that's just like looking at pictures, looking at values. First of all, you always look at the part density. Into part density, you can see an influence that with the second setup, we have a part density over 99.9%, very good, everything's great. With the first one, with the initial one, there is a little bit of movement, but in the end, we still have over 99.7% part density. I mean, we heard a lot of talks today that was, or the last days. Some people might think that it's still fine, but then looking at the material properties, you see that there's a high influence looking at the exposure order. So with the second shielding gas flow, always above 650 HV, not a lot of variation. And here with this first setup, you see an immense drop right in the beginning after exposing the first few samples, even worse with the exposure strategy with the shielding gas flow. Why is that? Well, looking at the melt pool depth, yeah, we can see directly that it's correlating. A steady melt pool depth for the setup 2, but with setup 1, we have the same kind of drop in the beginning. Looking at the picture, it's very obvious. So same process parameters for all of those 15 specimens, and very high influence seems over the exposure strategy or the build position, the part position. I mean, that's a correlation of the hardness and the melt pool depth. You can see with smaller melt pool depth, smaller hardness, higher melt pool depth, higher hardness. Seems to be a little bit of a transition phase in between. But what we see is this material is very sensitive to the shielding gas flow, and therefore we need to process those kinds of materials. We need to have a steady shielding gas flow to be reliable and reproducible with our material. Some EVSD images, but yeah, I think I have a little bit of time. Okay, already talking a lot faster than I thought. The hardness was very pronounced. You can really see the difference there. With the EVSD image, you can see a difference as well. Yeah, right. So you have the sample number 1 with the deeper melt pool depth in the middle of the part. You look at this, you still see the epitextural grain growth, but little larger grains maybe. And with the sample 15 with the wider or shallower melt pools, you see smaller grains mostly, and a more pronounced grain growth in the direction. So that's already it, because talking about materials, we really want to investigate what is the influence of the elements we are using. And now that we have a shielding gas flow that we think produces reliable results, looking at the carbon content of HS6-5-3-8. Why would we increase an already very high carbon content steel? Well, it was the question about, is it even possible to add carbon with rapid alloy development in such a steel? That was one research question we had, but another one was carbon is known for being austenitic stabilizing, and one hypothesis is that if we increase the austenite, or if we have austenitic stabilization, the martensitic setting temperature lowers, and maybe we can decrease cracking. Because with a martensitic setting temperature of about like 200 degrees, which would be the one for this steel, it might be the reason why it's cracking. So increasing the carbon content to see if we could prevent cracking. Already saying that it doesn't help, but still it's interesting in terms of scientific, from a scientific view. And that was a work in collaboration with Philip and Eric of Max Planck Institute. How did we do it? We used elemental powder, carbon, but not graphite, which is usually used, graphene, I think, but more, it's called glass-like carbon, which should be more stable, especially if you talk about mechanical alloying, which we did. So we used mechanical alloying. We heard it from Markus in the previous talk by planetary ball mill, and added 1% of carbon. So that's the highest amount that we added, and we have the 2 lower sets as well. And we saw that it was quite feasible. And looking at the chemical composition, we even see that the carbon content that we wanted to achieve was even achieved with the powder, within the powder, but also within the samples. So the highest deviation we have in the sample with 1.0% added carbon, and we saw in the process that we have a lot of spatters around, and we think that because of the fine grains, some of the carbon was transferred by shielding gas flow. So yeah, already mentioned it, no surprise for everyone, I guess. Cracking was not prevented, but induced was something that we expected, and something when we already have crack-free specimen in the beginning, how would we prevent it even? But it was just like looking into it, if it's feasible or not. So why is it cracking? That is the interesting question. And looking into the material, we first determined the hardness. And what is interesting is with higher carbon content, we lower the hardness of the material. I will talk about it in a minute because I have to hurry up a little bit. We see that in the microstructure, we have a grain refinement by adding 0.3 to 1.0% carbon content, a grain refinement, and a lot of carbides. I don't show the XRD analysis here, but we know they are carbides. This is the reference, this is the standard HS6-5-3-8. We see a lot of retained austenite already, so by about 50 to 60%. A lot of ferrite or martensite. Yeah, we didn't do a further investigation, so it's just BCC or FCC. But also, and this is something very crucial, a lot of not identified areas. So not taking, so that's really a lot. So we really have to be careful with interpreting the results of the phase content of retained austenite and martensite. But this result is very, very clear. When adding 1% carbon, we have a nearly fully retained austenite structure, which is interesting because we're talking about high-speed steel, but we were able to generate a fully austenitic microstructure. And in the end, and I think in the paper it's a little bit more written and explained and so on, but we think there are two mechanisms that influences the hardness and also the cracking of high-speed steels. While with increased carbon content, we increase the carbides in our material, obviously, that can increase the hardness. But by stabilizing the matrix with retained austenite, we lower the hardness. So that way, that's the reason why we have a lower hardness by increasing carbon content. But if you think about post-processing or the whole process chain with heat treatment, then might be even possible to obviously increase the hardness compared to standard dies, compared to the reference. In the end, for us, and that's something where the conclusion and summary comes up, for us it was interesting, elemental powder blend works, retained austenite is not the key, and it's interesting to use the elemental powder blends in LPBF for investigating new materials. But the first thing I think is even more crucial when investigating new materials, when investigating new process parameters, really looking at your system technology. What are you using? Is it reliable, repeatable, the results you're generating before going very, very deep into the material science, looking at the process you're doing. Yeah, so with that, I would like to thank you for your attention.